So not even sure how necessary it is for me to record this little bit here, but today we're going to be doing notes over periodic trends. These are the patterns that are found on the periodic table. There are plenty of other trends that are on the periodic table beyond the 4 or 5 that we're going to mention here today. And for all of these trends, we're going to take the periodic table and we're going to imagine that we're starting at hydrogen and work out from there. The first slide in the notes you don't need to copy down, but I kind of describe that process and describe how we're going to go through the notes. This is actually a video that I recorded for chemistry class where they cover a lot more trends than what you guys are going to cover, and I've just cut out the trends that you don't need to know, and we're left with the trends that you do need to know. For most of the trends that you need to know, you should know that the pattern is there, but to be honest, I'd use the periodic table itself to help with the pattern more than the trend. There are a couple trends here that we've mentioned before that we are going to repeat and re-emphasize, and the big oddball one is atom size. I believe in the upcoming video I say that I'll explain it in class, and I'm actually going to record another clip here in just a moment where I'll explain it right here. But you will need to pause frequently, so just raise your hand and let whoever knows in here and is playing the video for you to pause the video so that you have time to jot down the notes that are in each slide. In chemistry class, I go through these things very quickly because they're watching them on their own time where they can pause me as they wish. So pause me, jot down the notes when you're through. You can hit play again, and be sure if you have any questions that you jot them down, since you obviously can't ask me that right now. Anyway, with that, the title slide's going to say that these are Chem notes, but these have been edited to be your notes. Like I said, I cut out the stuff that you don't need, and I'll see you on the other side. So here we're going to look at the periodic trends. The real strength of the periodic table is not that it has these families and these groups or this weird shape, but that we can use this weird shape and the properties of the elements that are arranged on the periodic table to predict things that are going to happen. Because Mendeleev again showed us that there are certain repeating patterns, and those are called the periodic trends. And we get that from his periodic law. When atoms are arranged according to, now we know, increasing atomic number instead of increasing atomic mass, but increasing atomic number, there's a regular repeating pattern of the elements' properties. That is, certain properties repeat over and over again. What this means, generally speaking, is that things in a column tend to have one particular property, and things in a row, you can see that property change and shift. The next stuff here on this slide, don't jot down, but basically, with one exception, we'll assume that we're starting at hydrogen. We'll define a property, and then I'm going to describe the periodic table as we go across and as we go down the periodic table. I have it typed up. I recommend you do something like drawing it out on a double arrow, and feel free to abbreviate however you like. We'll start out with some simple ones that are kind of super obvious that you would not use a trend to do. I would not memorize these first few trends. I would not pay attention to the trend because it's more obvious if you just look at the periodic table, but I do it to establish the pattern of how the other ones are going to do, the other ones that are harder to think through or intuitively think about. As a side note, I have learned the definitions of these different properties that we're going to do, and I have learned a couple patterns, and from those patterns I reason out all the others. I do not memorize these things, and I discourage you from doing the same. So starting out, atomic number is simply the number of protons for a neutral atom. It's also the number of electrons. As you go across the periodic table, it increases by 1. And as you go down the periodic table, it simply increases. Here on the side, I'll have graphics of what this looks like or some of the data. You'll do a lab where you'll actually plot some of this data at some point. Next, for atomic mass or weight, it's simply how heavy it is. As we've said previously, is the sum of the protons and the neutrons. Here, as we go across, it usually goes up, and as we go down, it always goes up. And I apologize that the arrow is over top of the word here. And there are a couple exceptions to this. One of the exceptions that I happen to know that stands out to me is actually split in between rows. But as you go across the third period here, you hit argon and then potassium, calcium, and the masses go 40, 39, 40 as you go across like that. There's a brief little dip there with potassium where the mass goes down. There's another one over here, if I remember correctly, it's tellurium iodine region, where the mass goes down by a couple. It never goes down by a lot, and certainly as you go down the periodic table, the mass always goes up. Number of valence electrons is the number of electrons in the outermost energy level. Ignoring the transition metals here, as we go across, it increases by 1. As we go down, it stays the same. For charge of the ions, the pattern is very similar. The charge is a result of gaining or losing electrons. Again, here we're ignoring the transition metals, but as we go across, it's positive and increasing, and then negative and decreasing. And what I mean by that is it starts out positive, and we increase. We go 1, 2, 3, 4. Then at 4, the sign switches to negative, and then starts decreasing, 4, 3, 2, 1, 0. And so the charge of the ions, 1 plus 2 plus 3 plus 4 plus or minus, minus 3, minus 2, minus 1, 0 as you go across the columns, which means as you go down a column, they are the same. Now we start to get into the ones that aren't as intuitive, aren't as easy to think about. And this one here is to me, the most important one to memorize, because if you can remember this one, you can logic out the rest. So atomic size or radius is simply the measure of the size of the atom. Usually it's measured from the nucleus to the outermost energy level, and it is an estimate based off of the size of the whole atom, the radius there. And there are different ways to measure the radius, but as long as you're sticking with one method of measurement, this pattern holds no matter which method of measurement you use for all the atoms. So this one, it's easier to describe the down than it is to describe the across. Down, as you go down, it increases, and that should make sense because as we go down, we're getting more and more rings, more and more shells, orbitals where the electrons are. And so the atom size is going to increase as you go down. Remember, the size of the nucleus has very little effect on the overall size of the atom because the atom is so tiny and the space between the nucleus and the electron rings are so big and empty. However, as you go across the periodic table, you might say, well, it's the same number of rings, so it's going to stay the same. But it doesn't, and it doesn't increase, which is the other gut instinct to say, oh, we're going across, we're adding things, we're adding electrons, we're adding protons, we're probably adding neutrons, it must increase. It does not. As you go across the periodic table, the atomic size actually decreases. So as we go down, it increases. As we go across, it decreases. And this is counterintuitive, but is probably the most important one of these trends to learn. I'll explain in class why in full this happens, but it's easier if you can see it, and I'm not sure that the recording here is the best place for me to emphasize this. And the last one, and this one here is the only one that where we're not going to start at hydrogen for the trend because the trend is different for metals and nonmetals. But we'll still go the across and down pattern. It's just that we're technically not starting at hydrogen for this one because at least there's a pair of patterns here instead of just one pattern. Anyway, for metals in general, reactivity decreases as you go across and increases as you go down. And again, that goes to how readily they give up an electron and how many electrons they need to give up and how easy it is to give up those electrons. For nonmetals, the pattern is opposite because they're wanting to gain electrons, and so the pattern is exactly opposite. As you go across, it increases, and as you go down, it decreases. Through the magic of editing, here I am again at the end with the wardrobe I had at the beginning and different than what I was wearing in the middle there. So anyway, we need to explain atom size. And anyway, if you take a look at the periodic table, at the top row, you have hydrogen and helium, just two elements in the top row. And we're going to use those to explain atomic size. Now, this is true for other atoms, but in other rows of the periodic table, but they're the simplest ones. Before we do that, though, I'm going to quickly draw here, and the drawing will actually might not be all that quick, but as we go down the periodic table, we mentioned that the size is increasing, that it's getting bigger and bigger as we go down, and that should be obvious because we've already done electron configurations. And if we start with hydrogen, hydrogen has one energy level, and then underneath hydrogen there is lithium, and lithium has two energy levels. And so then it's getting bigger as we keep going down. Sodium, and you saw lithium and sodium react in the demonstration yesterday, but we have sodium with 3 energy levels, and potassium, which is the highest electron configurations that, well, next to highest electron configuration that we did in class, hit the highest energy level that we're going to deal with, which has 4 energy levels. And so then, not very circular there on the last one, but they get bigger as we go down the periodic table. And if we continue down to rubidium, or cesium, or francium, or the theoretical inium, then they would get bigger and bigger and bigger as we go down. So going down the periodic table, that's pretty obvious that they get bigger. It's the across that's awkward. As we go across the periodic table, the hydrogen to helium, why does helium shrink by comparison? As we go across the periodic table, and these are not to scale. In the lab the other day, you guys actually graphed these, and you had the actual numbers for the sizes of different elements, and you saw these patterns, that as you went down the periodic table, they got bigger. As you went across the periodic table, they got smaller. But I'm going to try to explain why. So, if you look at the periodic table, you'll see that hydrogen has an atomic number of 1, and helium has an atomic number of 2. Of course, atomic number tells us the number of protons and the number of electrons. So number of protons and number of electrons. And that's why we end up with a smaller size. Because what ends up happening is the protons, of course, as you know, are in the center. They're in the nucleus. The electrons, on the other hand, are on the outside, and they are orbiting around the nucleus. Again, not to scale. So hydrogen has 1 proton in the center, and we're going to pretend that that's that, and 1 electron, and that 1 electron goes around. And 1 electron feels the pull of 1 proton in the center. As we go across the periodic table, we get to helium. Helium has 2 protons in the center. It also usually has 2 neutrons that don't have any effect on this at all, but we'll go ahead and toss them in there. And it has 2 electrons that orbit around the outside. So in the center there are 2 protons, and there are 2 electrons. Well, it's not that 1 proton pulls on 1 electron and 1 proton pulls on the other electron, and each electron feels the pull of its own proton. No, those mean old protons in the center, they gang up on that electron, and both protons pull on that electron. And on the other electron, both protons pull on that electron, and so then the electrons feel the pull of all of the nucleus. These electrons feel the pull of all the nucleus, and so then they feel more pull pulling them in, and that makes those energy levels get smaller. And so then the orbitals end up being whatever they are, but they are smaller and closer into the nucleus as you go across the periodic table, because everywhere on the periodic table, as we go across, you're getting more and more protons in the center, but the electrons are left on their own to fend for themselves on the outside edge as they orbit around. And so as they orbit around, they don't help one another out, they don't protect one another from the protons to any significant extent, but the protons in the center, they gang up on those electrons, and they make it so that these electrons feel the full pull of the full nucleus, and that's what makes atoms smaller as you go across the periodic table. This particular trend in and of itself doesn't make a ton of sense, but if you think through it like this, then it does make sense as to why this happens, and it is incredibly important for almost every other periodic trend, including reactivity and why elements get more or less reactive. As you go down the periodic table, that electron is getting further and further away from the center, and because of that, the center has a weaker and weaker hold on it, and so then metals get more reactive as you go down the periodic table. As you go across the periodic table, you go from atoms that want to lose their electrons to over on the other side. Helium doesn't want to lose any, but if you go underneath helium, you have neon, and next to neon, you have fluorine, and fluorine wants electrons more than any other element on the periodic table. And as you go across there, because fluorine only has those 2 energy levels, and they're closer into the center, because fluorine is smaller as you go across the periodic table, it pull it only wants one more. It's got 7 already. It wants one more, and it's easier for it to pull that one extra in because it's got this very strong nucleus close to the outer edge. As you go down the periodic table and you get to the larger atoms, they still want to pull in electrons, but they can't do it as easily as well as what fluorine can. And that's just the reactivity trend. There are at least a half a dozen other major trends on the periodic table that we've not even touched on here, and atomic size is really the reason for many, if not all, of those other trends. And so this is an incredibly important trend for you to know. It gives you gorgeous graphs like you saw the other day in the lab, and really, like I said, it's a little bit it's not what you would think immediately, but it is something that you can easily reason through. Anyway, that finishes it for the notes today. If you have any questions, be sure you jot them down and bring them with you next time to class.